We have till now completed the electrophilic substitution reaction of benzene. So, now we will start some other reactions of benzene and we will study a very important property of the benzene substitutions and we will then end this chapter. Okay, so let's start. So, the next type of reaction of benzene is addition reactions. We have earlier said that benzene rings seldom undergo addition reactions. They generally undergo electrophilic substitution, but addition reaction is possible at extreme conditions, that is high temperature, high pressure, catalyst or light. Under these conditions, benzene ring can undergo addition reactions. So, the first example of addition reaction is hydrogenation. Okay. So, we have benzene and we add 3 hydrogen in the presence of nickel catalyst and heat. In this reaction, all the double bonds of benzene will be reduced. We had benzene. By catalytic hydrogenation of benzene, we get cyclohexane. Okay. The second example of addition reaction of benzene is halogenation. We add 3Cl2. This reaction is carried out under UV light and heat. So, in these conditions, this compound is formed. Okay. So, in this one, when excess electrophile was introduced, the double bonds were still intact. So, this was electrophilic substitution. Okay. Double bonds are intact. So, this is substitution, since double bond remains intact. But in this case, double bonds have been reduced. So, this is addition. Okay. The next type of reaction is combustion. Okay. So, combustion of benzene forms carbon dioxide and water. Okay. Now, when we were studying about alkanes and alkenes, we had studied about combustion. We had read some general formulas. So, the general formula for alkanes is CnH2n plus 2 plus 3n plus 1 by 2, these many oxygens, and we get NCO2 plus n plus 1 hydrogen. For alkenes, we have this general formula CnH2n plus 3n by 2 oxygen, it will give NCO2 plus N water. Okay. For alkynes, the general formula is CnH2n minus 2 plus 3n minus 1 by 2 oxygen, and we have NCO2 plus N minus 1 water. Now, by combining all these general formulas, we get a formula which is applicable for all hydrocarbons, that is CXHY plus X plus Y by 4 oxygen will give XCO2 plus Y by 2 water. So, this is applicable for all hydrocarbons. Okay. So, by this formula, we can also calculate the combustion of benzene. Okay. So, we have this formula. Okay. Benzene is C6H6. So, here X equal to 6, Y equal to 6. Now, X plus Y by 4. So, 6 plus 6 by 4. 6 by 4 is 3 by 2. So, we have 15 by 2 oxygen, and we have XCO2, that is 6 CO2 plus we will get Y by 2 water. Y was 6. So, 6 by 2 means 3 water. Okay. So, if we balance the both sides, 6 carbon, 6 carbon, 6 hydrogen, 6 hydrogen, 15 by 2 O2. Therefore, there were 15 oxygen atoms. So, we have 12 plus 3, 15 oxygen atoms. So, this is the equation for the combustion of benzene. Now, let us check if we can use this formula for alkanes, alkenes and alkynes as well. So, for alkanes, let us take ethane, C2H6 plus X is 2, 2 plus 3 by 2. Okay. That is 7 by 2 oxygen gives 2 CO2 plus 3 H2O. Okay. Now, if we take ethene, C2H4, so we get 2 plus 1, that is 3 oxygen gives 2 CO2 plus 4 by 2, that is 2 water. If we take ethyne, C2H2 plus 2 plus 2 by 4, that is 2 plus half. So, we get 5 by 2 oxygen which gives 2 CO2 plus 2 by 2, that is 1 water. Now, if we do these reactions in terms of these formulas, then also we will get the similar reactions. So, this was the combustion for all hydrocarbons. Now, a very important property of benzene that has to be discussed is the directive influence of functional group. So, what does it mean by directive influence? So, let us say we already have a mono-substituted benzene. Now, we are introducing a second functional group to the benzene ring. So, we had read that di-substituted products of benzene can be ortho, meta or para. Ortho means 1, 2, meta means 1, 3 and para is 1, 4. But when we have a mono-substituted benzene, then the second substitution is not equal for all these positions. Okay, so ortho, meta and para isomers will not be formed in equal amount because one position will be favored over the other. So, in which position the second functional group will be introduced is decided by the first functional group that was already present in the benzene. Okay. So, this is called directive influence of functional groups. Directive influence of functional groups. Okay. So, further substitution of mono-substituted benzene depends on the group already present. Okay. So, there can be two possibilities. One is ortho-para and another is meta. Okay. So, first we will study ortho-para directing groups. So, ortho-para directing groups are those groups which increases electron density on ortho and para positions. Okay. So, such groups are OH, NH2, NHR, halogens, etc. OCH3, OR and alkyl groups. Okay. Basically, electron donating groups, but these are exceptions. These are not electron donating groups, but they are ortho-para directing. Okay. So, let's see one example and understand it. We have phenol. Okay. So, oxygen has lone pair So it goes like this. And a negative charge develops here. Now this can again go like this. So now this phenol is again revived. Okay. So let's see, in these three structures the negative charge is either in ortho or in para positions. Therefore, negative charge on ortho or para. Therefore, the electron density of ortho and para have increased. That is why now some electrophile is introduced, they will go to either ortho or para. So, therefore, these groups are ortho-para directing. The second type is meta-directing. So, meta-directing groups actually do not increase the electron density of meta position, they decrease the electron density of ortho and para. Okay. So, since they decrease electron density of ortho and para, so now meta has higher electron density. So, such groups are NO2, CO2H, CO2R, CHO, COR, SO3H, etc. That is mostly electron withdrawing groups, with an exception of halogens again, they are ortho-para directing. So, let us understand this one with one example. We have nitro. Okay. So, this double bond comes here and this forms resonance in the opposite direction. So, now we have a positive charge here. So, now this double bond will migrate. Positive charge here, again this, now positive charge here, so we get the nitro back. So, here see, the positive charge is introduced at ortho and para. Therefore, electron density of ortho and para have decreased so much that electrophiles cannot act here now, because in a position where positive charge is already there, electrophiles cannot react there. Therefore, electrophiles join on meta position. Okay. So, these are the meta directing group. So, with this we have completed the discussion of aromatic hydrocarbons. So, aromatic hydrocarbons are generally quite toxic, mostly the aromatic hydrocarbons where there are more than two benzene rings fused together, They are generally toxic. They are called polynuclear hydrocarbons. They are very toxic, and many of these compounds are cancer causing. So they are carcinogenic. So with this, we have completed the discussion of hydrocarbons. Thank you. Happy learning.